Very good morning to all of you. In the last lectures, we have studied about PCM and delta modulation. Now we will hold a discussion on some analytical aspects of this particular technique. We will derive the expression for noise in delta modulation. Also, we will discuss about some of the limitations of delta modulation and how some improvisations in the existing technique improve the performance of delta modulation. So in the sense, we are going to talk about adaptive delta modulation and differential delta modulation. So first of all, we will discuss some of the limitations of delta modulation. What are the limitations of delta modulation that need to be overcome using some improvised version of it? So for this, I need to draw some diagram, and I need to understand the slope overload error that is a main characteristic of delta modulation. And there are two types of slope overload errors: positive slope overload and negative slope overload. Both have been discussed in the previous lectures also, but in this lecture, I will try to make things clearer. Suppose you have a message signal like this. So let's call the signal MT, and you are going to approximate the signal using a staircase function with a particular step size. Suppose this is how the staircase function looks like, and you see this function is most of the part not able to approximate this particular message signal, and the approximation looks something like this. So this continuous signal was MT, the original signal, and this approximating staircase function was M cap t, and this is an example of positive slope overload. The waveform N cap t needs to closely follow the waveform MT. Only then the recovered waveform M cap t resembles MT. This figure shows a situation where the waveform N cap t is unable to follow MT because the slope MT is greater than the slope of this staircase function. So this slope is greater than slope of this staircase function. This is positive slope overload scenario. This results in an error. This is positive slope overload. Remember that in positive slope overload, slope of MT is greater than slope of approximating signal M cap t. Okay, we can have a different version of slope overload error. I'm going to discuss now negative slope overload error. Okay, so let this particular signal be MT, the original message signal. This is to be approximated using the staircase function with fixed step size. Uh, let's make it this, like this, like this. So please ignore the variation in the step size due to my handwriting, because I am assuming that it is fixed step size M cap t, approximating staircase function. So what is that relation between the slope of original message signal MT and N cap t? In this case, slopes are negative, and slope of MT is more negative than the slope of M cap t. In both cases, in case of positive slope overload and negative slope overload, there will be a distortion of the recorded waveform. So this is an example of negative slope overload. Negative slope overload, where slope of MT is smaller than slope of m cap t. In both cases, the DM system, the delta modulation system, is said to have slope overload. Now, suppose there is a very slow varying signal. A signal is varying very, very slowly. This is the MT, and we are trying to approximate it using a staircase function with a fixed step size. Something like this will emerge. Let's call it the approximating signal m cap t. Now, in this case, the amplitude changes less than a step size. So this is another kind of an error. The variation in MT are such that they are within the step size. Hence, the waveform m cap t is like a square wave. Now, if you try to recover the signal, this will be recovered as a DC signal, whereas the original signal MT is not DC. There is some variation. There is some variation, but the approximated signal using the staircase function with a fixed step size will be recovered as a DC. Thus, in this case also distortion is resulted and the noise is known as granular noise. So this is the case of granular noise. Granular noise. When amplitude changes less than step size. When the amplitude of MT changes less than the step size of the approximating staircase waveform. So these are prominently three types of errors that occur in conventional delta modulation systems. The limitations of delta modulation system can be overcome by suitably changing the step size. So what is our assumption here in all three cases, that the step size is fixed. If we can change the step size on the fly, slope overload can be overcome. This can be overcome if step size is increased in such a way that the magnitude of the slope of m cap t becomes greater than the magnitude of slope of mt, and when the signal variations are less than the step size may be reduced to take care of this situation. This kind of a mechanism is known as adaptive delta modulation. So now I'm going to clear this canvas and introduce you a typical block diagrammatic representation of an adaptive delta modulation system. We are now going to discuss adaptive delta modulation system in the block diagrammatic form. Okay, so let's start from the first block of this ADM system. The first block is a difference amplifier. Is a difference amplifier. So the input to the difference amplifier is our message signal MT, whose slope matters. Let the positive terminal be given that signal and the negative terminal be connected to some other part of the whole system. And this other part is nothing but an integrator, because we need to accumulate the amplitude values as we go on ahead in time. The output of this difference amplifier, which is delta t, is given as an input to the modulator. So this modulator is run by a pulse generator, and the output of this modulator, let's call it PO, which is a time varying signal, is sent on the communication channel. We have a variable gain amplifier, and there is a gain control input to run this variable gain amplifier, which comes from any square law device. There is a RC circuit. So this is a capacitor. There is a resistor here. This whole thing POT is again fed to a quantizer. From there, it again goes to a variable gain amplifier, run by a gain control input, which in turn is run by a square law device, and there is an RC circuit at this end also, and this circuit is matched with the circuit at the previous end. The output of the variable gain amplifier is again fed to an integrator, and finally to another low pass filter, which provides you the approximated signal N cap T. So let's call it M cap T instead of the other notation because it's different from typical delta modulation. So on the transmitter side, we have this variable gain amplifier. It is used before this integrator as its input. The gain of this amplifier depends on the gain control input, which is obtained by integrated this POT in an RC network. This RC network we're talking about, and passing the integrated output through this square law device. Under the slope overload condition, this POT is a long sequence of either positive or negative pulses. The RC integrator integrates these pulses. This integrator integrates these pulses. Thus, the output of this integrator is either a large positive or large negative value. The square law device output is of a large positive value irrespective of whether the input is positive or negative. Okay, because it's square law device. Thus, the gain control input of the variable gain amplifier is large and its gain increases. When the gain increases, the step size increases, which can then take care of the slope overload, positive or negative, any condition. When the signal variations are within the step size, this POT is a sequence of alternate positive and negative pulses. The RC integrator output in this case is 0, and hence the gain control input of the variable gain amplifier is also 0. The gain of the variable gain amplifier decreases, resulting in a reduced step size, which takes care of the situation. So in both cases, the step size is either increased or reduced based upon the gain of the variable gain amplifier. That happens at the transmitter side, this side. Now we come to the receiver. On the receiver side, the output of the quantizer is fed to the variable gain amplifier. This variable gain amplifier has a gain control input. This gain control input is derived from this integrator circuit, which is whose output is fed to this square law device. Thus, an adaptive adjustment of step size is obtained at the receiver also, and which results in an undistorted reception of the transmitted signal. So basically, it all revolves around this integrator in the transmitter side, this integrator at the receiver side, and the nature of POT. When there is positive slope overload condition or negative slope overload condition, POT is a long sequence of either positive or negative pulses. When there is no slope overload, it is a sequence of alternate positive and negative pulses, and that makes the difference. If it is a sequence of large positive or large negative values only, the RC will give a peculiar output. If it is alternating between positive and negative value, the output will be different, and the output in case is 0. Okay, so that is the logic behind adaptive delta modulation system. That solves the problem associated with conventional DM system when the step size is not adaptive. This easy implementation using a simple RC circuit and a square law device makes the step size adaptive, and it overcomes the limitations posed by traditional delta modulation system. Now we come to the analysis of noise in delta modulation. Let's now do analysis of noise in delta modulation system. We will be needing this analysis in solving numerical problems that will come later on. I am now clearing this canvas, and now we will do a derivation for obtaining the formula for quantization noise in delta modulation system. So noise in delta modulation system we are going to discuss now. Let's first talk about the most important term in delta modulation, that is the quantization error. The quantization error in delta modulation, that is given by this del t, which is the difference between the message signal and the approximating function, which is the staircase function. The maximum quantization error in delta modulation, as long as the slope overload is avoided, is S. So S is, you can write it here, the maximum quantization error as long as slope overload is avoided. Okay. In PCM, this thing is S by 2. In delta modulation, this is S. Now assume that this delta T, this quantization error, takes on all values between a particular voltage level, let's say minus S and plus S with equal likelihood. I should state this explicitly that this assumption is with equal likelihood. Then the probability density of del T, F del, is equal to 1 upon 2S. It is going to be the probability density. Since it is equal likelihood, then we are assuming a uniform probability density function. So this is the probability density function of del T. So if you have probability density function of a particular quantity, you can always calculate the normalized power, which is the signal squared. The area under the curve of the signal is the normalized power. And this is, while integrating from minus s to plus s, this quantization error squared multiplied by its probability density and integrated over the limit minus s to s. That is the normalized power of del t. This is normalized power of quantization error. That's a very important formula that we can write after some manipulation equal to this integral over this particular limit and upon 2s d delta. We have just substituted this value of f delta. F delta was 1 upon 2s. We have used this thing here and this comes out to be s square upon 3. Very important result. Noise in delta modulation system. Now it can be reasonably assumed that the frequency spectrum of del T is wide over the range 0 to FB, where FB is 1 upon tau, tau being the step duration. So the quantization noise power in this frequency range is S square by 3. Hence the output noise power in the baseband frequency range from 0 to any frequency FM, FM being the upper limit of the baseband frequency range, is going to be NQ is equal to S squared upon 3 Fm upon Fb, which becomes equal to finally 3Fb. Remember that Fb here is 1 upon tau and tau is the step duration. So that is also a very important result. So that was quantization noise in delta modulation. Now another topic of interest in trying to have an idea about the output signal power in delta modulation. What is the output signal power in delta modulation that we have discussed in the previous lecture also, and let's discuss it again for the sake of completeness so that the whole derivation is clear. We are now going to talk about output signal power in delta modulation. In PCM, the signal excursion limits are minus ms by 2 to plus ms by 2. So let's talk about PCM first. In PCM, we have this signal excursion limit to plus m to s by 2. So s here is step size and capital M here is number of quantization levels, that is number of quantization levels. But on the other hand, in DM, there is no such limit on the amplitude of signal waveform. Rather, there is a limitation on the slope of the signal waveform in order to avoid slope overload. So in DM, we are talking about the slope and not on the amplitude or quantization amplitude. So let the worst case signal power be concentrated in the upper end of the baseband be assumed. When the signal power is concentrated in the lower end of the baseband, that is when the signal waveform changes very slowly, there is nominally no limit to the signal power which may be transmitted. So we can write here that if we assume the message signal to be like this, where A is the amplitude and omega m equal to 2 pi fm, fm being the upper limit of the baseband frequency range, the output signal power which we are interested in, let's call it S naught. That will be given by m square t average, mean square value, is equal to a square by 2. Let's call it equation 1. The maximum slope of mt is what? The maximum slope of mt is omega ma. The maximum average slope of dm approximation in cap T is s upon tau. So there has to be a limiting value of a just before the start of the slope overload. So let's write two things here. Maximum slope of mt is what? The maximum slope of mt is equal to omega m a, and the maximum average slope of dm approximation m cap t is s upon tau is equal to s upon into fb, and at one point of time these two values need to be equal. That point of time there will be the start of slope overload. So the slope overload starts just when these things become equal. These two things become equal. So what should be the value of A at which these two things are equal? So A is equal to S into FB upon omega m when slope overload just starts. So let's put this value of A in the expression number 1. So let's call it expression number 2. Let's call it expression number 3 using 3 in 1. So I'm going to write it here. Using 3 in 1, we are going to put this value of S naught is equal to S square FB square upon 2 omega m square. That's the final expression for output signal power that we were interested in. Now, there's another quantity that we need to discuss, and that is I'm now going to clear this canvas and discuss a new quantity related to DM. New quantity of interest is output signal to quantization noise ratio. I'm going to discuss about output signal to quantization noise ratio, also denoted by S upon NQ for DM. So we have derived NQ in just now, just 10-15 minutes before, and in order to you to recall this, I'm writing it down directly that this was the NQ. This was the NQ, and this was S naught output signal. This was output signal. So we want a ratio of these two. So the ratio S naught upon NQ is given by S square FB square upon 2 omega M square into 3FB upon S square FM. So this FB multiplied with FB square becomes FB cube, and this S square gets cancelled out. We have 3 upon 8 pi square because omega m is 2 pi fm, and FB here and FM here and whole cube here. Okay, which is roughly equal to 3 upon 80 FB upon FM whole cube. So this is typical output signal to quantization noise ratio for a delta modulation system. We have now derived all popular relations related to PCM and DM. Now we are in a position to do some numericals. Thank you.